Assalamualaikum warahmatullahi ta'ala wabarakatuh. A very good day to everyone. Alright, so uh, still in topics fundamentals of thermodynamics. Okay, so before this we have discussed on the air standard cycle part 1. Okay, so basically this part 2 focusing on Otto cycle. Alright, so part 1 we have discussed on the reciprocating engine. Right, so part 2 we focus on the Otto cycle, which is the spark ignition engine. Okay, so in previous video also I have discussed on the 4-stroke, okay, and the basic understanding on the Otto cycle. Okay, so some example of Otto cycle also has been discussed in part 1. Okay, so part 2 we discuss on the 2-stroke spark ignition engine, which is the petrol engine. Okay, alright, so 2-stroke, so compared to previous is a 4-stroke. So 2-stroke is a no piston stroke for suction and exhaust operation. So suction is accomplished by air compressed in crankcase or by a blower. Okay, so basically we have a area here. So this is your suction, okay, by in the crankcase. Okay, so the induction of compressed air remove the product of combustion through exhaust port. Transfer port is there to supply the fresh charge into combustion chamber. Okay, so this is the normally we call it as a, here is an intake port. This is from your carburetor. So from your carburetor, the fresh air fuel mixture goes into the bottom part, which is below the crankshaft. Okay, so normally your petrol and air mixture also includes a 2T. Okay, so 2T oil, okay, is being mixed in a petrol and air mixture. So the 2T oil is used to lubricate the crankshaft. Okay, because no engine oil inside the crankshaft here. So the crankshaft is depend on the 2T oil. Alright, so the fresh mixture goes bottom here, while your piston here is being compressed in the induction. Okay, so the compressed mixture is being sparked by spark plug, okay, and combust. So therefore the piston will be moved down and the exhaust port is being released to the exhaust. Okay, on the other hand, at that same time the intake port is being closed by the piston. Okay, and the fresh air will move the combust air. Okay, so the new one is being mixed here, so together with the exhaust gas being transferred to the exhaust. Right, okay, so the 2-stroke engine are generally less efficient than their 4-stroke counterparts, but they are relatively simple and inexpensive, and they have high power to weight and power to volume ratio. Okay, this is the difference between 4-stroke and 2-stroke, where your 4-stroke we have in one cycle we have 4-stroke, which is 2 revolution. 1 stroke your crankshaft will rotate at 180 degree. So which means that for 2-stroke the crankshaft will rotate at 360 degree. Okay, for 4-stroke your crankshaft will rotate 720 degree for one cycle. Okay, so 2-stroke is only take half of it, which means that the crankshaft only rotate 360 degree to complete one cycle. Okay, for PV diagram is much similar with 2-stroke engine, 4-stroke engine, whereby process 1, 2 is isentropic compression. Okay, process 2, 3 heat addition at constant volume, 3 to 4 is an isentropic expansion, whereby your exhaust gas being released to the open. Okay, and 4.1 is your constant volume heat rejection. So this is your exhaust, all of your exhaust gas is released to the exhaust. Okay, this is the direct comparison 4-stroke and 2-stroke engine. So for 4-stroke, we have 4 stroke of the piston and 2 revolution of crankshaft, which means that your crankshaft will rotate 720 degree, while your 2-stroke engine, 1 revolution crankshaft of 360 degree. Okay, so from 4-stroke, we have 1 power stroke for every 1 cycle, or for every 2 revolution of crankshaft, while 2-stroke we have 1 power stroke for each revolution of crankshaft. Okay, so 4-stroke engine have heavier flywheel, while 2-stroke engine have lighter flywheel. 4-stroke engine, due to 4 stroke in 1 cycle, so the power produced is less compared to 2-stroke engine. In theoretically, the power produced is twice, because 1 complete cycle is only 2 stroke. So 4-stroke engine heavier and bulky because it compromise of valve. Okay, but for 2-stroke engine is much more light and compact because it's only use a revolve. Okay, 2-stroke engine don't have any valve. Alright, and it's much more simpler, especially in the cylinder head. Alright, okay, for number 6, lesser cooling and lubrication requirement. But for 2-stroke engine, greater cooling and lubricant requirement, as 2-stroke require 2T oil, but for 4-stroke engine only require engine oil. So 2-stroke require 2 types of engine oil, which is 2T and 4T. Okay, so number 7, for 4-stroke engine, lesser rate of wear and tear. For 2-stroke engine, higher rate of wear and tear because of the high revolution. Number 8, contain valve and valve mechanism. For 2-stroke engine is only port, intake port and exhaust port. So number 9, higher initial cost, especially on the time engine. For 2-stroke engine, cheaper because it does not have any timing chain and valve and camshaft. Okay, so number 10, volumetric efficiency is more due to greater time of induction, while for 2-stroke engine, volumetric efficiency is less due to lesser time of induction. So number 11, thermal efficiency is high because consists of intake valve and exhaust valve. But for 2-stroke engine, the thermal efficiency is much lower because the port is normally open. Okay, and much losses inside that intake and exhaust port. Okay, so number 12, it used where efficiency is important, but for 2-stroke it is used where low cost, compactness and lightweight are important. So 4-stroke engine normally is for bigger vehicles such as buses, truck, tractors and industrial engine, whereby 2-stroke engine is for lawn mower, potong rumput, okay, scooter, motorcycle moped macam Waisuku, and propulsion ship. Okay, IC engine performance parameter. The job of an internal combustion engine is to convert heat energy into mechanical energy. Practically, it means that an IC engine of any types produce mechanical work in the form of a rotating shaft, giving some torque at some value of RPM, revolution per minute, by continuously burning of fuel. Performance of IC engine means that How will it complete the above mentioned job? It can be measured or compared only in terms of certain parameters, and it's called performance parameter. The performance of the engine is judged from the various parameters. The basic engine performance are torque, engine power, air fuel ratio, and lastly, brake specific fuel consumption, BSFC. So these performance parameters are normally plotted against engine speed and usually used to compare between IC engines. Engine torques. So torque, moment or moment of force, is the tendency of a force to rotate an object around an axis or a fulcrum or a pivot. So engine torque is the amount of turning power produced by an engine at its flywheel. So it is measured by using engine dynamometer and calculated as your torque, okay, forces exerted, okay, times your length or the radius. Okay, so this is your normally length, so this is your force exert. Okay, so this is your length toward your force exert for the flywheel or brake drum. Okay, so normally torque unit in Newton meter. So torque is a work other than Newton meter, is also known as joule. Engine brake power. An IC engine is used to produce mechanical power by combustion of fuel. Power is referred to as the rate at which work is done. Power is expressed as the product of force and linear velocity of product of torque and angular velocity. In order to measure power, one needs to measure torque or force and speed. The force or torque is measured by dynamometer and speed by tachometer. The power developed by an engine and measured at the output shaft is called the brake power, BP, and the formula is given by BP 2 pi n number of revolution times torque divided by 60,000. So the unit is in kilowatt. Alright, so basically here you can see torque is unit in Newton meter or joule. So in order to convert joule into watt, you require joule divided by second. So second comes from number of revolution, n. So that n, number of revolution, normally is measured by engine speed or RPM. Okay, so this RPM have a revolution per minute, okay, have a times. So one need to convert the minutes into second. So that's why we have 60,000. Okay. Air fuel ratio. Air fuel ratio is the mass ratio of air to fuel present in a combustion process, such as in an internal combustion engine. So air fuel ratio. So the air is on top, fuel is at the bottom. So air is the mass, okay, and fuel also is a mass. Okay, if the mass flow, so we have a mass flow rate, m dot. Okay, either mass or mass flow rate, neither can be used, right? So the stoichiometric ratio is the ideal ratio of air to fuel that burns all fuel with no excess air. For gasoline fuel, the stoichiometric air fuel mixture is about 14.7 to 1. For example, for every 1 gram of fuel, 14.7 grams of air are required to complete the burning or to complete the combustion. So air fuel ratio of 12 to 1 is considered as maximum output ratio, whereas the air fuel ratio of 14.7 to 1 is considered as the maximum fuel economy ratio. So normally for normal vehicle, the range for air fuel ratio is from 12 to 1 to 14.7 to 1. Okay, so mass of air can be calculated through ideal gas law, PV-MRT, or by using air flow meter. Mass of fuel can be calculated through the weight of the fuel tank or fuel regulator. Brake specific fuel consumption, BSFC. BSFC is a measure of how efficiently a given amount of fuel being converted into a specific amount of horsepower. So more broadly stated, it could also be considered a measure of combustion efficiency. So the BSFC is given by, so this is your formula. So the mass of fuel divided by your engine performance in kilowatt times your this is the unit conversion. Okay, so at the end you got the units BSFC is in gram per kilowatt hour. Okay, alright, so this is the example of IC engine performance curve. So you see that in x-axis this is the engine speed, so this is the direct comparison. So the engine speed is a normal. If you see any engine performance curve, normally the x-axis is based on the RPM. So normally in a y-axis you have a horsepower. So normally at bottom part we have a fuel consumption or air fuel ratio. So this is top, we call it as a engine torque. Okay, the middle one we call it as the horsepower. So if you see that engine speed is from 1000 to 2400. So normally for a vehicle of, let's say, a car, nowadays the engine maximum speed RPM is about more than 7 to 8000 RPM. For motorcycle is much more. For example, for a moped, let's say Waisuku, it can up to 12,000 RPM, the maximum capacity. Sample problem 5.2. Okay, sample problem 5.2. An Otto cycle having a compression ratio of 9 to 1 use air as the working fluid. Initially, P1, pressure 1, is at 95 kPa, kilopascal, T1, 17 degrees C, and V1 is 0.312 liters. Okay. During the heat addition process, 3.75 kilojoule of heat are added. Using constant specific heat values at room temperature, determine all the temperature and pressure at each stage, the thermal efficiency, and the mean effective pressure. Okay, so basically, so we have 5.2. Okay, alright, so draw a PV diagram. Okay, so PV diagram. Okay, so basically 1, 2, process number 2, this is your process number 3, and this is your 3, okay, this is your 4. Okay, so given P1 is 95 kPa. T1 is at 17 degrees Celsius, and also V1 is 0.312 liter. Okay, so basically liter here you need to convert into meter cube per kg for because normally here we use a liter meter cube per kg, which is your specific specific volume, in order to ease the calculation. Okay, so we have a Q in here. Okay, so Q in is at 3.75 kilojoule. Okay, alright. So here is your V min. So this is your V max. Okay, because we only have two volume, and this is a constant volume. This process also constant volume. Okay, because this is a straight line. Okay, vertical straight line. So basically we know that vertical straight line is a constant volume. Okay, so we have two volume only. Alright, so from this figure we need to determine the temperature and pressure, okay, for each state. Okay, 1, 2, process 1, 2. Okay, so from here we need to convert also. P1 given directly 95 kPa. T1 is 17 degrees C. Okay, V1 is 0.312 liter. So we need to convert into meter cube. Okay, so 1 meter cube over 1000 liter. Okay, so you can get your meter cube. Okay, so if given kg, okay, so we can determine the meter cube per kg. If not, we need to determine first lah. Okay, so for process 1, 2, in order to determine the kg, in order to have meter cube per kg, so PV, P1, V1 is MRT1. Okay, so M, okay, is P1 V1 over RT1. Okay, so P1 given, V1 also given. Okay, what else? R, universal gas constant, R. Okay, so you can check at room temperature, so you get something around 0.287. okay, kPa dot meter cube per kg dot K. Alright, so here is Kelvin, K, sorry, meter cube Kelvin. Okay, so Kelvin here, so we need to convert your temperature into from Celsius into Kelvin. Okay, so it's okay, we have all the values, so it's around 0.000356 kg. Okay, alright. So from this we can get your specific volume. Okay, so meter cube per kg. Okay, so your value here, okay, divided by 0.000356 kg. This is a meter cube, so you got in meter cube per kg. Okay, alright, so we can use this value V, specific volume V1. Okay, and then from here, what is the correlation between 1 to 2? Okay, So 1 to 2, we can know that is a, okay, so 1 to 2 is a isentropic compression. So from isentropic compression, okay, so we can know that in order to determine at point 2, pressure and temperature at point 2, okay, so T2 over T1 is V1 over V2, K minus 1. Okay, V1 over V2 is a compression ratio. Okay, so we can get 9.1 K minus 1. Okay, alright, so T2, okay, Kelvin. Okay, alright, so you can determine by yourself lah. Okay, for P2, okay, P1 over P2 is V2 over V1 K. Okay, so it's also same. This is a compression ratio, but is at bottom. So the ratio is at bottom. So 1.4. So you can get your P2. Okay, you got your Kp. Okay. Alright. So we have, as the question is to determine the pressure and temperature for point. Okay, we have P1 and P2. Okay. What else? Okay. So point number 3. Okay. So 2, 3. Alright. So what is the correlation between 2 and 3? Is a heat addition. So heat addition, okay, given also Q in is 3.75, okay, kilojoule. Okay, so basically here in this question, this amount of heat injected Q in is particularly quite high. Okay, so you can, in order to solve this question, you will have a temperature so very high. In reality, if this amount of heat being added, your engine will be melt down. Okay, because it's so high. But this is an exercise, so basically calculate only lah. Okay, we just calculate. Okay, so Q in is constant volume, so mass constant volume, CV constant volume, T3 minus T2 is 3.75 kilojoule. Okay, so we got T2, we have CV is CV constant volume, CV is 0.718. Okay, so this you can determine at appendix. Okay, mass we have calculated. Okay, the mass. Okay, so from here, okay, so basically this is 3.75 given directly. Okay, so T2 we have calculated before, and T3 is we need to find. CV is 0.725, and mass we have calculated before at 0.00365. Okay, so we can calculate 0.000356 times, okay, 0.718. okay, so T3 minus T2 is at 3.75 kilojoule. Okay, so T3 Kelvin. Okay, So basically your T3 is quite high. Okay. Alright. So we have temperature. So we need to determine the T3. We got P3. Okay. So P3. Okay. So constant heat addition. Okay. Also constant volume. Okay. So P3 V3 MRT3. Okay, this is for 2 and 3. P2 V2 and MRT2. Okay, so constant volume. Okay, process 2 and 3 also constant volume. So we got cancel out. R also is similar. We cancel out. M also cancel out. So we got what we got is only P3 T3 P2 T2. Okay, so P3 we have calculated. So P3 kPa. Okay. Alright. So we got the P3. So 2 and 3 we have finished. So we move on into 3 to 4. Okay. So 3 to 4 is much similar with 1 to 3 because it's a centropic expansion. It's not compression, but it's expansion. Okay. So basically we have using expansion. So P3 over P4 is V4 over V3. Okay, K. Alright, so basically V4 and V3 is similar. Okay, because the acentropic compression. Okay, so basically it's similar with V2 over V1. Okay, K is at 9.1 over K 1.4. Okay, so P4 we can get lah KPA. Okay, so be surprised. P3 is quite high, very high, and P4 we can recheck. It's near the value of P2 because the point is near to P2 somewhere. So you can recheck that this value is near to P2. It's not exact, but near to P2. Pressure at point 2. Okay, so we have all. Sorry, what you got again? T4. Okay, T3 we got P3 P4. Okay, T4. Okay, T4 per T3 is equal to V3 per V4. Okay, K minus 1. Okay, so 1 over 9.1 K minus 1. Okay, so we got T3. So T4 kPa. Sorry, Kelvin. Okay, alright. So from here we got all the value required, temperature and pressure. Okay, so the question is to find, the first question is to find, wait, where is the question? Okay, to find the thermal efficiency. Okay, thermal efficiency. So this is the Otto cycle. So efficiency is 1 minus 1 over R K minus 1. Okay, so 1 minus 1 over 9.1. Okay, 1.4 minus 1. Okay, so you can get around 58.67. Okay, alright. So the B, mean effective pressure, MEP. So MEP, mean effective pressure, is net work net per V max minus V min. Okay, so V max and V min. Okay, so V max, you should know that V max is V2. Okay, V min V1, specific volume. Okay, specific volume. Okay, alright, so we can rearrange work net is V specific volume. Okay, 1 minus 1 over R C, compression ratio. Okay, so here we can get your mean effective pressure in kPa. Okay, as work net Q in minus Q out. Q out. Okay, so Q in is given directly 3.75 kilojoule. Q out is M CV T4 minus T1. Okay, so we have all. Okay, so we can calculate lah. Okay, alright, thank you.